In the previous video, which was about an example where you got a saddle point for a system of two differential equations, two linear differential equations, which we thought of in vector form, resulting in a 2 by 2 matrix A, we got that the origin was a saddle point. As a practical matter, when you did your eigenvalue computations, that meant that one of the eigenvalues was positive and one was negative. In this video, we'll consider a different example. dy dt equals this matrix, whose entries are -4, 1, 2, and -3, times y, as our example, and see what happens. First thing to do, as always, is to think about whether the origin is the unique equilibrium point or not. Just in your head, I won't bother writing it down, you should take the determinant of this matrix. 12 minus 2 is 10, that's non-zero, so the only equilibrium solution is at the origin. And the origin is always an equilibrium solution for a linear system like this. Next, it's on to the eigenvalues and eigenvectors. In that previous video that you should have watched before this one, the saddle point example one, I derived a formula that you can always use for the eigenvalues in terms of the determinant and the trace of the original matrix, A. We have had enough experience with the determinant that you probably remember that is AD minus BC. The trace is the sum of the entries on the main diagonal. I'll call the determinant D and the trace T, and here's the formula for the two eigenvalues. Lambda equals t, the trace, plus or minus the square root of t squared minus 4d over 2. You should make sure you review that video because you are responsible for understanding the derivation of this formula. It comes from the quadratic formula, but you notice it does look a little different. For one thing, we don't use the letters A, B, and C like you see in the quadratic formula. For another thing, there's not a 2 times something else down here. There's a t instead of a negative t up there. So there are some differences that result when we actually apply the quadratic formula. So I'll use this here now. And anytime you have a homework problem, you may use this formula, unless I explicitly say to derive it using the determinant equation for the eigenvalues, using the characteristic polynomial. You can use this. Sometimes it might be easier just to get the characteristic polynomial and factor it, but in this case it's probably best to go ahead and use this formula. The trace is -7, plus or minus the trace squared is 49, minus 4 times the determinant. We already saw the determinant was 10. And we get a square root of 9 in there, so this problem works out nicely, as these examples that I'm doing here will. There could be some cases where you will get numbers under the square root that are not perfect squares, and technically speaking, you should be able to handle those cases. And the book does do some examples. But for the sake of time and just focusing on the concept, I've made these numbers to work out nicely. So one root is going to be -7 plus 3 over 2, that'll be -2. And the other root will be -7 minus 3 over 2, that'll be -5. So now we have two real roots that are both negative. That's going to result in the origin being called something called a sink. All solutions will approach the origin as t goes to infinity. It'll be sort of like when we look at the phase plane, we imagine it's a bunch of water, and the water, sort of the molecules follow the solution curves in toward the origin, and the origin, in a sense, kind of sucks them all up. That's what we imagine. Once we've got the eigenvalues, if we're going to write the general solution, however, we need to find the eigenvectors. The shortcut way of doing so that I showed you in that saddle point example video was to think of this equation in another way, to think of it as A minus lambda I, where I is the 2 by 2 identity matrix, times V equals 0. And so go ahead and replace lambda with -2 and then -5. Write down the resulting system of scalar equations and solve it. So I'll go up here, I'll imagine taking the -4 right there and subtracting -2, which is equivalent to adding 2 to get a -2x. Leave that coefficient as it is because it's on the off diagonal, plus y equals 0. Now go to the second row, leave that one as it is because it's on the off diagonal, 2x, but then take -3 and subtract -2 to get -1. The resulting system of equations should be redundant so that you get non-trivial solutions. We can then take either one of these equations and solve for y in terms of x or vice versa. And then pick something, in this case for x. I'll label these lambda 1 and v1. Something non-zero. If x is 1, then y is forced to be 2. But I could have picked some other non-zero number. The second eigenvalue is -5. -4 minus -5 is +1. So I get an x. Keep the 1 up there the same. Its coefficient of the y is then 1. That 2 stays the same. I get a 2x. And you should predict what we're going to get here. We should get a +2y equals 0. So these equations are redundant. And you get -3 minus -5, which is +2. So once again, we get a redundant system. And if you don't, that's a way to check that you did something wrong. Let's take this one, solve for y in terms of x, and we get y equals -x. And so the eigenvectors for the eigenvalue -5 are along the line through that non-zero vector, if we put its base at the origin. So our general solution looks like this. An arbitrary constant times e to the lambda 1t, which will be -2t, times v1, the vector 1, 2, plus k2 e to the lambda 2, -5t, times the vector v2. And you'll see if you look at the saddle point video that I can put this in a couple different forms. I, for example, can combine these vectors into one vector. I think since I basically want to focus just on this one example in this video, we might as well go ahead and solve an initial value problem. Let's assume y of 0 is the vector 3, 4. So we're starting at that point when t equals 0. Going back to my solution from the previous slide, I plug in t equals 0 and imagine combining the vectors, and that's going to give me the following system of equations in the unknowns k1 and k2. Since e to the 0 is 1, I'll get a k1 times 1 again, plus k2 times 1 times 1 again. I'll get k1 plus k2 equals the first component of this vector, 3. Going to the second component up here, plugging in t equals 0, I get a 2k1, and then a minus k2 equals the second component of this vector, it equals 4. So I need to solve this system for k1 and k2. This should not be a redundant system. It should have a unique solution. If it doesn't, you did something wrong. We know from the existence uniqueness theorem that these linear systems certainly have unique solutions for initial value problems. You can solve this any way you want. Probably the quickest way to solve this is to just add the two equations because the k2's cancel. If they didn't cancel, then you could multiply one of the equations by something appropriate to get the k2's to cancel when you add them. Or you can do substitution. So it looks like we have k1 equal to 7/3. Use either one of these equations to solve for k2. I'll use the bottom equation. k2 is going to be 2k1, 2 times 7/3 minus 4. I'm imagining putting the k2 on the other side of this equation and subtracting 4. So I get 14/3 minus 12/3, or 2/3 for the value of k2. And then, yeah, you should write down your final answer. Y of t, the unique solution of the initial value problem, will be 7/3 e to the negative 2t times 1, 2, plus 2/3 e to the negative 5t times the vector 1, negative 1. You'll also see in your reading that, I won't take the time for this right now, but you'll also see in your reading that the books want you to be able to, and I also want you to be able to take this vector solution and find the individual components and draw their graphs, and also be able to go back and forth between the phase plane, the graph of the solution in the phase plane, and the graph of x versus t and y versus t, those scalar functions, individually, and be able to see the relationship between the two. Let's go ahead and draw the phase plane and maybe highlight this particular solution, if we can. First, don't forget about making a big dot for your equilibrium solution to emphasize that it is an equilibrium solution. It's a sink. All the solution curves approach the origin as t goes to infinity, so I'll draw on a bunch of curves with arrows pointing toward the origin. But you do need to be careful to get some subtleties right. First of all, it's good to draw in straight line solutions. We have straight line solutions along the eigenline, the eigenspace, through the vector 1, 2, whose tip would be right about there if we put its base at the origin. This line is going to consist of straight line solutions. Go straight toward the origin as t increases. That's along the eigenvector 1, 2 for the eigenvalue negative 2. And we also have an eigenvector 1, negative 1 for the eigenvalue negative 5. So you get straight line solutions along that line, going toward the origin as t increases. The final thing to draw is the other solutions, and this is the most subtle part. Let's think about what's going on here with this function as t increases. Imagine that both k1 and k2 are non-zero. As t increases, both of these terms are going towards 0. But because that's a negative 5t as opposed to a negative 2t over here, this one goes to 0 a lot faster than this one, relatively speaking. Of course, they're both going to 0 very fast, but on a relative scale, if you are talking about orders of magnitude, how many times smaller is this one than that one? Ultimately, as t goes to infinity, this one, relatively speaking, is getting a lot smaller, a lot faster than this one is. What does that mean? What's the practical consequence of that? It means that along that eigenvector, the solutions go towards 0 faster than along that one. This was the eigenvector for negative 5. I guess technically that eigenvector would be down here. The solutions are going to go to, if you start with an initial condition, say up here, the solution is going to go, in a sense, be pulled toward the origin by both of these lines, in a sense, but along this eigenvector, that component is going to go towards 0 a lot faster. And so what you end up getting is the solution curve actually being tangent to the line of eigenvectors for the other eigenvalue that's closer to 0. think about what's happening to those two terms in the general solution for a curve like this, in a sense, it's like you've got a different coordinate system in a sense, and the component of the solution in this direction here is going to zero much faster than the component in this direction. And that's an intuitive reason why you approach the origin tangent to the line of eigenvectors for the solution, for the eigenvalue that's closer to 0. And you could draw in some other curves, and you probably should. Some other ones like this to emphasize how it's going. The book gives you an example where they prove using limits that you approach this line, and you should study that. I'm not going to take the time in this video to go through that, but you should make sure you study that. They remark that it seems like you should use L'Hopital's rule to find a particular limit that they get, but L'Hopital's rule sort of leads you astray. You can't really use it effectively. And so you've got to do a little trick by multiplying the top and the bottom of the fraction that they analyze by a certain exponential to get it into a form where you can take the limit. But this is a sinc, and you should make sure you label it as a sinc. And speaking of sinks, that reminds me of a joke. A mathematician was not very good at home improvement, and well, one day his toilet was breaking down, and so he called the plumber, and the plumber came and fixed the toilet, and the mathematician was just very happy and elated, but then the plumber gave the mathematician the bill. And the mathematician said, "Oh, that's 1/3 of my monthly salary. How can I possibly afford that?" And, well, you know, he was upset, but he eventually scraped together the money and paid the plumber. But the plumber did feel sorry for the mathematician and said, "You know, why don't you come to plumber school and learn how to be a plumber, and you can apply for a job as a plumber in my company." So the mathematician thought about it and decided that sounded good, especially when the plumber told him that he would earn 3 times as much as he did being a mathematician at a local university. So the mathematician decided to become a plumber, went through plumbing school and became a plumber, and was earning lots of money and was very happy. But I forgot to say, the plumber told him when he was applying for the job that he shouldn't tell the company that he was a professor, that he had a PhD. That most plumbers, this is not meant to denigrate plumbers, but most plumbers in his company at least hadn't gotten past the 7th grade. Sorry about that. That's part of the joke. Anyway, so the mathematician didn't say that, but eventually the company decided that all their plumbers should at least complete the 8th grade. And so they were all sent back to school, and the mathematician, if he wanted to keep the job, had to go back to school also. And it just so happened that the first class that they had was math. And the teacher was up at the board trying to test the students' knowledge, and the teacher said, "All right, who knows the formula for the area of a circle?" And nobody raised their hands, but the teacher decided to call on the mathematician and had the mathematician come up to the board, and I guess the mathematician was a little bit excited to be able to use his math, but when he got up to the board, a funny thing happened. He had forgotten the formula for the area of a circle. And so he proceeded to try to figure it out. And he scribbled all across the board a bunch of calculus equations, integrals and derivatives, to try to re-derive the formula for the area of a circle. And every time he did it, he kept getting negative pi r squared. This frustrated him. He, of course, had this intuitive gut feeling that that shouldn't be the answer. It should at least be a positive area, so he kept redoing it, and after about 20 minutes or so, he was about ready to give up, and he turned to the rest of the plumbers in the class in desperation, and they all sort of tried to whisper to him, "Switch the limits on the integrals." He forgot to do that.